Hello. Testing, testing, test. Hello. Good evening, guys. Can you hear my voice clearly? I'm not sure if this microphone is working properly. So can you hear my voice in the microphone? Yes? No? Okay, never mind. So tonight, I'll be your guest lecturer today. My name is Bopeng, and I'm a little bit introduction of myself today. I am the guest lecturer of tonight's class, and I have got, like you guys, I have been studying in PolyU. I got my PhD in this university with Professor Jiang. And before my years at PolyU, I spent a couple years in the United States for my master's degree, and also with a couple working years in a local wastewater treatment plant in Washington, D.C. So tonight, I'm very honored to be the guest lecturer of tonight and introducing you guys with a little bit of the wastewater treatment. Tonight's class will be a very fundamental introduction of the wastewater treatment and some wastewater, and we will be covering 3 topics tonight. And the first one is what is in wastewater. So the wastewater characteristics, and know that what's in the wastewater, then we have an idea on how to treat the wastewater, and that is the general process that we'll be talking about. And lastly, the third topic would be effluent standards. That is, to what extent shall we treat the wastewater and and discharge them into natural water bodies. So also for now, a little bit more information about myself. And now I'm working at AECOM as engineer for the design of wastewater treatment plant. So I will give you a brief introduction of AECOM later. So the first part of tonight's class will be wastewater characteristics. What's in wastewater? So the corresponding of this class will be chapter 2 of our textbook, the wastewater engineering, treatment, and resource recovery. And this is published by AECOM. That is where I'm working now. So personally, I strongly recommend you to finish the corresponding reading of this wastewater engineering chapter 2, because to me, this wastewater engineering, this textbook is not only a design guidelines for students. They're also a textbook for like professionals. Even now, when I'm working as a wastewater engineer for designing wastewater treatment plants, I still need to refer to this book for some guidelines to have some ideas of what I am doing and find some solutions. Therefore, I know it's going to be a lot of reading in this book, and I really hope that you can finish the reading and understand what we'll be talking about. And after reading this chapter 2, and you have a better understanding of what we will be going through tonight. Also, a little bit introduction of AECOM. That's the company I am working on now. So AECOM is a wastewater. It's a engineering designing consulting company. It's a global. It provides like a engineering design to global market, and it also plays a very significant role in the Hong Kong local market in delivering the design of wastewater treatment plants. So I will introduce some of our projects that we've been doing in our company, and then I will. So moving on. So the first part of tonight. So what is wastewater? So although wastewater is called wastewater, but indeed it's 99% of water plus impurities. So these impurities could be insoluble particulates like suspended solids. Like the bottle you see right here, the solid is suspended, and the clear one as a contract. And also we have soluble solutes in the wastewater, such as ammonium ions, some dissolved organics, nitrate ions. So for these impurities water, they have a very wide range of particle distributions. They have some large debris that in micrometer scale that we can see by naked eyes, such as sand and grit, algae, flux, large organic debris, and these can be seen by our naked eye. And as the size get into nanometer scale, and these such as like cell fragments, bacteria, they cannot be seen by our naked eyes. However, they are not dissolved in water; they're still suspended, colloid. As the size getting smaller, and also other than the particulate part, we also have some dissolved fraction that's even smaller size, like metal ions, vitamins, carbohydrate, fatty acid, proteins, etc. So the major source of wastewater would be from 3 major sources, like domestic wastewater, just like the water we use every day, such as like when you wash a shower, generating wastewater, wash your dishes, generating wastewater, wash your hands, generating wastewater, and go to the washroom, generating wastewater. And these were all collected by the sewer system and conveyed to the wastewater treatment plant for further treatment. And also we have wastewater industrial. We also have industrial wastewater, such as the processed water they use for making their products, such as food industry and livestock industry. And the last part would be stormwater intrusion. Imagine when it's raining, so all the runoff from urban runoff or like in the forest, they threw some water conveying pipes or some drainage. They flow through the landscape and to the receiving water body. So these would be the 3 major sources of wastewater. So for these sources of wastewater, then we have we can generally divide them into 2 principal sources of pollutants. That is non-point source and non-point source and point source wastewater. So the point source is that the wastewater collected by networks of pipelines, just as the wastewater generating in our household. When you wash your hands, the wastewater go into the sewer and collected, and they are conveyed through pumping station or by gravity. They flow through the pipeline and to a single point, mostly in wastewater treatment plants. For non-point source is for example, when it's raining, this water, raining in the city, the water polluted flow over the surface of the land and along the drainage and to some receiving water bodies, and possibly also to some stormwater pipelines that we are designed to collect this wastewater. So here you have a list of a pollutant category that we'll be talking about tonight, and after today's class, you will have an idea of why they have different potential of water pollution of different categories. So in wastewater treatment, we have a few of major contaminants to be removed. And some of these, like grit, large solids, suspended particles, bacteria, odor, color, it's very easy to imagine based on our daily usage experience with water. When you use your water, you wouldn't see something suspended in the water, or like you don't want to smell anything from water or see any unusual color. So this is very easy to understand. Some other things like organic matter, specific chemicals, after tonight's learning, we'll have more understanding of what's going on there. So let me introduce you about these contaminants to be removed in wastewater treatment. So the first one would be grit and other larger solids. So by definition, grit, they are some heavy mineral materials such as sand and gravel. Here you can see the picture of the rags being caught by the stack spring in wastewater treatment plant. And this it's called rags, cannot be treated by further treatment processes. So they are typically physically removed from the wastewater. And the problem of discrete materials is that they are hardly to be treated by by the following biological treatment process of wastewater, and also they can accumulate in the following treatment pipeline, and also cause some like a mechanical abrasion to the equipment such as pumps, blowers, and pipelines, and cause some issues in the operation and maintenance of the mechanical equipment. So typically they are removed by physical methods like screening, heat chamber sedimentation, and also some filtration possibly. So after the large colloids, large size particles, we have some smaller size particles called suspended solids. So TSS, this includes some silt or clay particles, smaller algae, fine organic debris, and some particulate matter. So you can see here with a higher concentration of TSS, so that means more suspended solid in the water, and we can have a higher turbidity of the water, and that's not what we want. If we are using, we would like prefer a clear water when we use them and when we discharge them from wastewater treatment plants. So typical methods to measure the concentration of TSS will be used by vacuum filtration apparatus. Here we have a filter paper, and they will be set into this in the middle of this apparatus, and we have water pumping going through the water filter paper. And here we have a vacuum turning on, and all the water is sucked over the membrane, and with the water passing through the filter paper, and the suspended solids retained on the filter paper. Then we can then we know how to quantify the amount of suspended solids. So organic matters, organic pollutants is a very important target to be removed in wastewater treatment. So typically organics in wastewater the compositions are proteins, carbohydrates, and fat and oils. So these things, they are the major source of these things is from our food waste and also human feces. So this is the major sources of these organics in wastewater, particularly in municipal wastewater. So that's household wastewater. So in this material, and also in wastewater, we have some trace organic compounds such as urea from our urine, pesticides from some agricultural use, surfactants from the kitchen cleaning stuffs, and also some other like organics from the household products that we have been using in our daily life. So the problem of organic is that because in wastewater there will be a lot of microorganisms. Remember, a lot of microorganisms exist in the wastewater, and when these organics are decomposed into the wastewater streamline, they have a higher energetic state in compared to the inorganic matter that is carbon dioxide. So these microorganisms can use these organics. That is, in simple words, is that the microorganisms like human, they like to eat and for their growth. So microbes use this organics in wastewater, capture the energy by converting these organics into carbon dioxide, and then use this energy for their own cell growth and maintain their daily life. So this process is called respiration, and will consume oxygen. So consumes oxygen. So when it consumes oxygen, the problem is that we would like to keep the aqueous system into oxygenated aerobic conditions. Because this oxygen, if in a natural water system, they are to be used by fish and other organisms for their living. But if the microorganisms with the additional organic waste dump into the water, so the microbes use the oxygen, and there's not enough oxygen for the fish or other microorganisms in the water, and the fish will die, and the anaerobic bacteria will take over, have some smelly byproducts on the water system. That's not what we consider undesirable. So let's look at this oxygen sac to have a better understanding what we're talking about. So here you can see here we have the dissolved oxygen. So it is at an equilibrium between the water body and the atmosphere. So the atmosphere water is dissolving, and also some oxygen leaving the water bodies. So with the decomposition zone, then we have organics being dumped into the water body, and we have increase of organic concentration, and the microbes start to use oxygen and to decompose the organics. And then the oxygen level goes down. In this zone, the decomposition zone, then we don't have enough oxygen for the other microorganisms to live in this zone. So as the organics being consumed and the oxidation reach the lowest point, and here is the septic zone where it's not good enough for other microbes or other organisms to live in this region. And then with the organics being consumed and the oxygen replenished from the atmosphere is faster than the oxygen consumption rate, then we have a slow buildup of the oxygen back to the normal line. And after the organics are consumed, the recovery zone, then we have oxygen back to normal level and back to when other microbes and organisms can live in this area. So this is the problem that when we have organics disposed into the water system. So now we know that for the organics being dumped into the water system, how do we quantify them? So here we use the concept of oxygen demand. Oxygen demand is how much oxygen is needed to oxidize the carbon from organic carbon to carbon dioxide at its most oxidized state. And also we have the nitrogen in the wastewater, and the organic nitrogen from ammonia to nitrite. How do they happen? So the oxidation, we can consider it happening at two stages. The first stage would be carbonaceous oxidation. So here in wastewater, the organics in wastewater, we typically use the fundamental elements to represent them: the carbon, hydrogen, oxygen, nitrogen. So think about the composition of protein, carbohydrate, fat, and oils that we just talked about. So these would be the fundamentals. But the organics in wastewater is super mixture of many different organic compounds. So we will not know the exact composition of it. So here we use this chemical formula to represent the organics. So the first stage, carbonaceous oxidation. So it's when we oxidize the organic carbon to carbon dioxide only. But the nitrogen here remains unoxidized. So the oxidation state of nitrogen is still -3 to -3 here of ammonia. So this stage 1 is only the oxidation of organic carbon to carbon dioxide. So in stage 2, the oxidation would be nitrogenous oxidation. So we have the ammonia being oxidized to the nitrite and nitrate eventually. So here the oxidation state of ammonia from -3 becomes +5, that's being oxidized. So here let's look at the sample to have a better understanding. So now we have consider that we have an oxidation of acetic acid, CH3COH. So or in this general form of C2H4O2, and we don't have nitrogen in this case. So that's the case we will have. So the oxidation of this is very simple chemistry of the mass balance. The carbon is carbon, and the carbon should be balanced, oxygen to be balanced, hydrogen to be balanced. So in this formula, you just need to balance the formula, and you have the numbers over there, and here numbers here. And so if we let's see if I can plug in the numbers here. Okay, so here we have 2 carbon here, then we plus 2 here, and hydrogen and 4 hydrogen, and just based on simple mass balance, the basic chemistry, and you will have the formula like this. So now with the oxidation, now we know the concept of oxidation demand, and then we can move on to the next step is the biochemical oxidation demand, or say biological oxygen demand, BOD. So what is BOD? BOD is that we use microorganisms to oxidize the organic matter, and how much of oxygen is used by these microorganisms for decomposing the organics. So BOD test is a very common test for wastewater characterization, and from the formulas we know how to do it, but in practice, how do we measure the BOD concentration? So the BOD test is a very straightforward process. So we just need to put the sample of wastewater and feed in with a population of bacteria, and we monitor how the oxygen level changes. Then we know how much of the organics will be in the wastewater. So here we look at the picture. This picture is showing the jar test for BOD test. So you see here we have samples of wastewater, or a series of dilutions of the wastewater in bottle, and we need to add in some inorganic nutrients and a pH buffer to maintain the best conditions for the growth of bacteria, and also we put in the seed of bacteria from a sewage treatment plant, and then you will have then we just leave them over there and monitor the dissolved oxygen concentration over time, and then we will know how much of oxygen is being consumed by the microorganisms. So if you get a chance to do the experiment, so this would be the typical, this result is typically expected over the amount of oxygen being consumed over the time. So in the initial phase, but remember that this shape what we're expecting from BOD test is only like representing the carbonaceous oxidation that we are just talking about. So it's only the organic carbon being oxidized to carbon dioxide, and the nitrogen is not here. If we have organic nitrogen in the wastewater, then we will expect another spike of the oxygen demand here, because the difference what we see here is that there are two groups of the microorganisms doing the oxidation. So here for the blue line is the carbonaceous oxidation. This is a heterotrophic bacteria, but for the green line showing here is the oxidation of ammonia to nitrite and nitrate. That is the another group of bacteria doing nitrogen nitrification. So the concept to make it clear is that the BOD, or say BODL or UBOD, the ultimate biological oxygen demand, is representing the ultimate carbonaceous biological oxygen demand. So it only refers to the microbes, the biodegradable carbonaceous organic carbon to carbon dioxide. The oxidation of ammonia is not including BOD. So, but the problem of the BOD test is generally it takes too long for the experiment to be done. So typically, like you can perform the BOD test in 5 days, 7 days, or even longer. And also from the figure that we show here, it is not practical for us to wait until the time reaches infinite. Then we can read the ultimate BOD value over here. Therefore, so the solution to this problem is that we use a model to calculate for oxygen consumed versus time a kinetic equation to calculate the ultimate carbonaceous BODL. So the formula showing here, you can find the details. If you're interested in the derivation of this formula, you can refer to our textbook in chapter 2, and you'll find the solutions there. And if you have any questions, we can discuss later on. And here, yes, back to the equation here. So BODT refers to the oxygen consumed after T time. So in practical, when we do the BOD test, we typically have a standard incubation period of 5 days. The performance, so BOD5 will be here, plugged in here. The L is the UBOD that we want to know, and with the equation here, and the K is the rate constant of the bacteria consumption rate of the organic matter. So in here, if we have a wastewater sample, the best way to determine the K is by experiment. But if we don't have a sample, but in the designing phase, then we can assume a K of 2.23, and this is a typical value from experience at 20 degrees Celsius. So if looking at the example, if we want to use this equation to calculate BOD5, so we just need to plug in the number. So ultimate BOD is 200 milligram per liter, is plugged into the L over here, and then we have the K is 0.23 and T is 5 days at 20 degrees Celsius. Just plug in the number, and then you can get the number of BOD5 in this case. So other than BOD test, we also have other methods to determine the organic concentration in wastewater. So the most commonly used alternative is COD test. So COD is chemical oxygen demand. So we can get a result in 2 to 3 hours. Then we have understanding of how much of organics is in the wastewater. So in this test, we use the dichromate and in an acid solution. Then we oxidize the organics into organic carbon dioxide. Then we can determine how much of organics is in the wastewater. So the difference between COD and BOD is that the COD test also includes those organics that cannot be biologically degraded. This part of organics cannot be used by microorganisms. Other than COD test, we also have the TOC test, total organic carbon. So this is done by an instrument, and it's a more intense process using a combustion process to oxidize the organic carbon and convert them into carbon dioxide and measure and then we can have an idea of how much organics in there. So TOC compared to COD include those organics cannot be oxidized by the dichromate. Therefore, it is more the value of TOC will be higher than COD, and COD will be higher than BOD in most cases. In general wastewater treatment, the most used parameters for us is typically the BOD test because it's BOD because most of the wastewater treatment process they are biologically based. So BOD is a very important parameters in our design. And also COD can be used as a reference to, if in a typical wastewater, they will have a relationship between COD and BOD. So with all the concepts of oxygen demand that we just know, and the fundamentals, we still be these two equations, that will be the carbonaceous oxidation and the nitrogenous oxidation. So once again, the carbonaceous oxidation is the organic carbon being oxidized to carbon dioxide, but the nitrogen remains unoxidized. The oxidation state of nitrogen is not changed. So stage 2 is nitrogenous oxidation, that is the ammonia being oxidized to nitrate. So here, the concept of theoretical, or say total oxygen demand, will be the combination of equation 1 and equation 2, the total oxygen required for complete oxidation of the organics. And theoretical chemical oxygen demand would be equal to oxygen required for equation 1, and theoretical nitrogenous oxygen demand would be the. So let's have a summary of these concepts. So consider we have the organics here, and theoretical oxygen demand is the total oxygen demand of the organics. So the fraction of the organics would be THCOD and THNOD, so carbonaceous oxidation and nitrogenous oxidation. So in THCOD, we also have the BODL. This part is only biodegradable. But not all the COD are biodegradable. This part is what we call non-biodegradable organics, or say like a refractory material. Similarly, in theoretical nitrogenous oxygen demand, they're also part of the nitrogen cannot be is not biodegradable. So THNOD will be the sum of the NOD and the refractory nitrogen in this part. So here, let's have an example and how we solve the equation here. So I think I can use the board over there, and we can solve this equation here all together. And okay. So you can try on these equations and see if you can solve by yourself. And we will be doing this together. So here we have C for so here we have carbon dioxide being produced, hydrogen being produced, and also ammonia. Here, ammonia, because this is the carbonaceous oxidation, only the first stage of the reaction. So to solve this problem, you just need to balance the equations here based on the mass balance. You have carbon, 4 carbon here, and oxygen and ammonia have 2 nitrogen, and plug 2 here, and the hydrogen you have 8, 4, and I think it's here. And then you have the equation. And with this equation, so with this equation, then you can use simple. You have the molecular weight of each samples of the organics, and you have the then you can calculate how much of the oxygen demand is required. So yes, which is not cool. It's 8, right? Oh yeah, sorry. Wait a minute. Okay. Oh yeah. Sorry about the mistake here. It should be 1. Yes. Have you figured this out? Yeah, right. So with this formula, then you can just the simple mass balance, and you can have an idea how much of the you have molecular weight of the carbon here, and you have the molecular weight of oxygen. You can calculate the oxygen demands here. So do you guys have an idea how to perform the following steps? You can have if you have questions solving this equation, you can raise your hand and let me know. Would you like me to go further and finish the equation and finish this example altogether, or you prefer we can move on? Okay, anyone got this number here? Okay, never mind. So, excuse me, do you got the number? Do you have the number? No? Yes? Anyone know, sorry, anyone know how to solve this equation? No? Yes? Just give me a nod. Okay, never mind, I'll just finish this. So some fundamentals of chemistry here over here, and what do I have here? Okay, so the molecular weight of oxygen. So here we have oxygen, it's 32 gram per mole plus 7. Then it's and for this C4H8, then we have the molecular weight of this. And now the equation that we have 100 milligram per liter of this chemical. So okay, so you have to. So here is the molecular is how much of oxygen is required for the reaction, and here you have the molecular weight of these organics that we are targeting, and here the 100 milligram per liter is what we have here, the concentration of organics in wastewater. And now with this equation, you can calculate how much of the carbonaceous oxidation demand is what we have in here, 97 milligram per liter, and you can try to reproduce the calculation yourself. And these are some fundamentals of chemistry, and also since here we are finding to ultimate biological oxygen demand, that would be, and this question has told us the compound is 80% biodegradable, so you just plus times 80%, then you have how much of BODL, ultimate BOD that we are looking for. So this is how you solve this example. So again, here this is only the part of carbonaceous oxidation of the organics, where the organic carbon being oxidized to carbon dioxide. The ammonia remains unoxidized. So here I have another in-class practice for you guys to perform it. And I would say I'll give you 5 minutes to solve this equation, and you can after these 5 minutes you can take a 10 minutes break, and we will be back in. Okay, let's continue at 7:21. Okay. Oh, 5 minutes. You have. Let's continue at 7:25. Let's come back to the class. You have 5 minutes for the practice. If you finished, feel free to leave the room, and you have 10 minutes break. We'll continue. We'll be back in 7:25. Okay. Okay. Okay, guys, anyone have a number? Anyone have a number for this equation, for this problem? You have a number? Sorry, what did you say? 141? So very close. Then you have the same issue with the units. So the answer to this question, so let's forget about all the details. I just tell you the number, and you have a question. If you have an issue solving this problem, you can come to me after class. So not good enough. Okay, so the answer would be this: if you have like this classmate, and then if you have a number of 142, something like that, and then maybe something wrong with the unit conversion, and if you have this number, that's great. If you don't have this number, don't worry. You can come to me after class. I can show you how to solve the equation. Okay, before I move on to the next class, I want to ask a question here. How many of you have ever been to a wastewater treatment plant? Anyone been to a wastewater treatment plant? No. Do you? So in this course, do you have a chance to have a site visit to the wastewater treatment plant in Hong Kong? No. Okay. So never mind. So that's a pity because like in wastewater treatment plant in Hong Kong, there's quite a few local wastewater treatment plant that is like developing many new technologies in treating the wastewater, which I will show you later on. So let's continue on our class. So moving on from organics, so what we have in the wastewater. So wastewater characteristics, pathogens, including bacteria, viruses, protozoa. These called pathogens because they can if intact by human, we can have some serious disease like diarrhea, having a fever, just like food poisoning, something like that. And so that's why we need to treat the bacteria, remove them from wastewater before we can discharge it. And another important constituents in wastewater is nutrients, nitrogen, especially nitrogen and phosphorus. So in phosphorus, these two nutrients, when they are discharged into natural water, they could cause a problem of eutrophication. So because the nutrients, nitrogen and phosphate, they are essential elements for the growth of microorganisms and some other organisms. So when they have overdose of the nitrogen and phosphorus into the water body, and we have overgrowth of the phytoplankton and the algae. So in here, when the algae dies and the microbes again decompose the organics and consumes the oxygen, and that is when the oxygen depletion happens, and this could be a dead zone for organisms. You see the dead fish in this zone if you have too many nutrients in the wastewater, and this is what it might look like in the water body when we have too many of the nutrients into the water. So for the removing of nutrients, in November we'll have another class dedicated for this process. So today we have a very brief introduction of the nitrogen and phosphorus in wastewater. So nitrogen has many. It's complex has different forms of nitrogen in wastewater, and the major form will be organic nitrogen and inorganic nitrogen. So the organic nitrogen is less oxidized with oxidation state of -3. The number goes up from -3 to 0 to +5. Then it has high oxidation states. They're more oxidized, and this is what the major forms are. The major forms of inorganic nitrogen is ammonia and ammonium, and these two will be in the discharge when the effluent is discharging. This will be a major concern of ammonia, and also the nitrate, and nitrogen gas. So phosphorus, the major form of phosphorus in wastewater could be orthophosphorus. Ortho means there's only one phosphate group. Polyphosphate, multiple phosphate group, and organic phosphate in a more complex form. So the orthophosphate is the easy form for organisms to use. They're soluble in water, and then we have a polyphosphate that's harder for the microbes to use them. They need to hydrolyze them to break them into a smaller orthophosphate before they can use them. So the decomposition of this one to orthophosphate takes some time. And organic phosphate is of minor concern in municipal wastewater. It will be more of a serious concern in industrial wastewater. So for these two parts, the nitrogen and phosphorus, we'll have another class in November to talk more about details of the nutrients in wastewater. So the last part is micropollutants. So micropollutants, including some other emerging contaminants that we are talking today. For example, here we have antibiotics. So from the drugs that we use, from the medicine that we use, and also some pesticides from agricultural use. So these are of particular concern in the specific industry. And also nowadays, the wastewater treatment in the industry, people are paying more attention to some emerging contaminants such as PFAS. It's a very hot topic in the United States. And microplastics is a trend over the world. And yeah, and antibiotics is also a trending topic. A lot of research is going on how to remove and what is the life cycle of these pollutants in wastewater. Okay, so now we have a basic understanding on what is in wastewater. So the next question is, how do we treat them? So what do we need to do, and use what process to treat the wastewater? So in the previous class with Professor Jiang, and the major focus was on the water treatment, I believe. And the difference between wastewater treatment and water treatment is that they have a very different source of the water coming into the plant. So for water treatment, the major source mostly would be some more clean water compared to wastewater, like river or some reservoir. So less compared to wastewater, much less the treatment process can be done here. So we have ozone, for example, and here the flocculation to settle down to help the suspended solids to settle down, and UV disinfection to kill the pathogens and bacteria in the water and for further use. But in wastewater, the raw sewage is more complex. It's many components that we just talked about. So in general, in wastewater treatment, we have 4 levels of treatment. So the preliminary treatment is the screening and grit removal, is to remove the large solids in the wastewater, because these large solids may deposit in the following treatment process, and also these large solids can cause some mechanical equipment issues. So if they damage the pump it's using to discharge or hurt the pipeline, and there's some serious issues in operation. And after preliminary treatment, removing the large solids, then we have primary treatment. Primary treatment is to settle solids, but in the smaller one, that's suspended, especially some organics, suspending organics in the primary sedimentation. And after that, we do the secondary treatment of biological treatment to use, in this case, we use the microbes to decompose the organics. And tertiary treatment will be the nutrient removal that we'll be talking about. And we have further filtration that will be further decrease the suspended solids in wastewater. And lastly will be the disinfection, sometimes ozone, UV disinfection or chlorine to chlorine to treat the water before discharge. So here is the typical flow diagrams of a wastewater treatment plant. So let's start with the beginning of the wastewater treatment. So preliminary treatment and primary treatment. So preliminary treatment, the first step is screening, or we say bar wax, or say core screens. I'll give you a brief introduction of this later. And grid chamber, equalization basing, and primary sedimentation. And this would be the fundamental flow. And for bar wax, what you see here, or we can call it core screen. So it's just basically a core screen here to stop the large debris going through to the following into the following treatment lines. So it's very simple physics removal of the large objects, and you could be either mechanically clean here. So when mechanical, it can be manually clean. So like this one, so operators need to come here time to time just to remove the large solids being stopped by this screen here. Or we have some mechanical clean screen, and we can have a video. I have a video here, then you can after you watch it have a better understanding of how this mechanically clean. So this is an example of mechanical clean products that we are using, and so they have different spacing of the bar. So here is the bar, and this is the rake. The rake is moving on, and so this will be the inflow water channel. As the wastewater coming in, you have suspended solids here, and this rake is moving up, and multiple rakes moving, and you can have the suspended solids and dispose. So just keep going up and down, up and down, up and down, and then this is how mechanical cleaning is working in removing the suspended solids. So here we can see some typical design information for the barbers that we use in wastewater treatment plant. So you can find this table also in the chapter 5 of our textbook. So you can see if you are doing some design works of wastewater treatment plant in the future, if you got a chance, you can always refer to our textbook. You will always have some. It's a very fundamental and comprehensive wastewater treatment designing reference. So some typical design parameter is the one thing for bar wax we need to pay attention to is the spacing between the bars. So for core screen could be for between 20 to 64 millimeter, and you have a larger spacing, then you have more solids can pass through the screen. And also approach velocity is also another important design parameters you need to consider, because if the approach velocity describes how fast the water is going through to your bar wax, to your screen. If it's too fast, you may have the solids going directly into your equipment and may damage your equipment, and also some solids might be like pressed through the bar wax entering the following treatment lines. But if the flow is too slow, then you have the solids that will deposit in the influent water channel, and then there's another concern. So here you can have a calculation how you calculate the influent channel that we just seen. So the W and D is the channel depth and rate. So for Q here is the flow rate of how much water is coming through your system to a wax, and the V is the approach velocity that we're talking about. You can use a typical design number of 0.6 millimeter per second, and then you can calculate. You have the S is the spacing. You can determine what kind of spacing that you can use in your system, and the bar thickness. With all these parameters all together, you can determine the dimension of the water channel in designing the bar wax. So in some treatment lines, this bar wax is called core screen. Then we also have another type of screen that with a smaller spacing that we can call it fine screen. So fine screen is typically with the spacing between the bars at 0.5 to 6 millimeter, and then this with a smaller spacing between the bars, and you can stop more of the solids. It really depends on it depends on what kind of treatment level you're looking at. And with more solids being stopped by the bar wax, you can also protect the equipment, mechanical equipment like pumps, pipeline, valves in the following treatment lines. So typically used bar wax are static screens, rotary drum screens, and vibrating screens. You can find some reference in our textbook as well, or some resource online. So following screening is grit traps. Grit trap is to remove this grit material, inert dense material such as sand, broken glasses pass through the bar wax, and some sealed pedals. And this is very important. We can avoid operation of pumps and other mechanical devices, the pipeline and the valves that I was talking about. So typically designed, commonly used grid chambers are rate grid chambers or vortex grid chambers. So rate means that we are pumping in the air, we are blowing oxygen, we are blowing air into the water channel. So here, for example, your rate grid chamber, you have water inlet in this direction, and on one side of the water channel, we have blowers, aerators, and blowing the air into the water channel. So this will create this circular form of water movement. So the solids, suspended solids, the large solids, they just with the water flow, they settle faster and settle down to the bottom and collected by this collection channel, and with the on top of here, and the wastewater can leave the channel to the following treatment lines. Another commonly used is vortex grid chamber. So vortex is similarly, it's also we have water coming in this direction and then turn 260 degrees and flow over here. So after it goes in here, because here we have a turn over here, and the grid will have a spiral form and move along with the water current, and because it's large solids, it will settle down, and we just learned from previous class in sedimentation. So also, again, these typical design parameters you can always find in our textbook and when you are solving your equations or solve your design issues. So after grid trap, it's primary sedimentation. So here this two figure on the right side, the primary sedimentation is a circular type of the primary sedimentation tank. So here with water, and you can see the mechanical equipment on the bottom. So what we're doing, so primary sedimentation is that we have water coming in, the solids settles down to the bottom of the tank, and then with this mechanical equipment, then we can remove the sludge on the bottom of it. And also we have a rectangular type, it's like this. So the water comes like this, and in here is also using the mechanical equipment. The solids settles to the bottom, and then we use this mechanical equipment, then we can remove them from the water system. So the goal of the primary sedimentation is to remove the organic particulate matter. Therefore, we can remove part of the BOD, the organics. So here, with a well-functioning primary sedimentation, we typically expect at least 30% of the BOD being removed in this process. So a very key design parameter of primary sedimentation is the overflow rate, because as figure showing here, you have the wastewater coming in at the bottom part of the sedimentation tank, and it's going upward and leave the tank at the top on top of the tanks. And the suspended particles, I think the fundamentals of the sedimentation you have already learned in a previous class. So a quick recap here is that the balance of the particles is balanced by the gravitational force, and you have a buoyancy of the particles, and also have a draft force from the water current. So only when the gravity wins, you can settle, right? So So here the flow rate is very, so therefore the overflow rate is very important for us to consider in the designing of sedimentation tank. If the overflow rate is too fast, then we have too much of the draft force, then the solids prefer not to deposit. But if the overflow is too slow, then the treatment capacity of the plant is being compromised. So we need to find a balance between the overflow rate and how much of the solids or organics that we try to remove. So typically we can consider like removing around 30 to 40% of the BOD and the excess of the suspended 40 to 60% of the suspended solids. And this depends on the wastewater characteristics, because different each plant have their unique characteristics, the different composition of the wastewater, the suspended solids, how much was in there. So it will be designed varied from each plant. There's no one rule from each other. So after primary sedimentation, we have equalization tank. We could have this is an optional one. Equalization tank in simple words is just a big water tank that to store waters. So equalization is just a storage tank, because the wastewater is not always coming into the wastewater treatment plant at a constant flow rate, right? So there will be peak hours for us. For example, for peak hours when we use the water. For example, when you get up in the morning, wash your face, brush your teeth, etc. So do the cleaning, then you have peak hours in the morning. And in the daytime when everybody goes to work, then we have less wastewater generated. And in the evening when everybody goes home, and then you take a shower and do a cooking, and then you use a lot of water, and that's when that's why the water generating is not always like at a constant rate. So you have patterns. So the function of equalization tank is to balance the quantity and quality of wastewater. So you have storage tank, all the water coming in, and then it's mixed well together, and have an average concentration, and then to provide adequate organic fluctuations to the following biological treatment systems and continuous feed to the systems. Therefore, the following treatment process is performing at a more like a optimum condition. So here is like the equalization tank is optional, depends on land availability as well. So taking Hong Kong for example, Hong Kong, in most of the wastewater treatment plants being constructed in Hong Kong, they all have the same issue of like a site constraints. We don't have too much lands for all the treatment tanks, so sometimes we have to eliminate the equalization tank. So after primary treatment would be secondary treatment. So secondary treatment is the organics removal, and it's all for the removal of soluble, biodegradable oxygen, organics, and also some suspended solids, because some of the organics are in form of the particulate form, not dissolved in water. So how do we accomplish the secondary treatment? It's typically done by microorganisms. So we use microorganisms to convert these organics into stabilized compounds. Just a recall to our concept, just learn the carbonaceous oxidation and nitrogenous oxidation. So the organic carbon being oxidized to carbon dioxide and nitrogen being oxidized to nitrate, and that's how it's done. So here is a callback to there. Here, these organics, the respiration process, you have the organics being oxidized to carbon dioxide. And this process, the respiration process, is an energy-yielding process. It generates energy. The microbes, when they oxidize the organics, they have energy, and they use this energy with these organics as well. And then some of them are used for their own cell growth and also for their cell maintenance. So here is again the carbonaceous oxidation, the organic carbon oxidized to carbon dioxide only. And the following is the ammonia oxidation to nitrite, and eventually to nitrate. So nitrite is +3 oxidation state, and nitrate is +5. So this reaction process is an energy yielding process. They involve the oxidation of organics by a specific group of bacteria. So for the carbonaceous oxidation and the nitrogenous oxidation, there are different groups of bacteria is working. So this energy yielding reactions is said to be exergonic. So for the basic requirements of biological treatment, so we need to have, what we need is a high density of microorganisms in there, and also have enough of oxygen, of course, for them to perform the degradation, and also a good contact between the organisms and the waste. That is a well mixing. That means we want them to be contacting all the time. A good mixing could be done aeration or it can be done by mixer. So also the form of organic waste is also important. Some of them are in the readily biodegradable form. They are soluble in water and they can be directly used by the organisms. This will be a much faster reactions of the degradation of the organics. And also some form of the organics, they are in particulate form. They need to be hydrolyzed by the organism first and decomposed into some simple forms and dissolved in water, and then can be used by the organisms. And all this also we need to create a favorable temperature, pH, nutrients, all these fundamentals for organisms to survive and to live at their optimal conditions, and no toxic chemicals, of course. So for biological treatment in general, they have two types of the biological treatment process. One is called suspended growth. So suspended growth is in the form that the microorganisms, they're suspended in the wastewater, not attaching to the surface of any media. So here we are looking, for example, activated sludge. So here we have an example of activated sludge. So the sludge now in this photo is settled down to the bottom of the cylinder. And if it's in a reactor tank, there will be aeration or mixing, and then you'll be suspended in the water, and you don't see this clear supernatant over here. It will be a homogeneous mixture, and that's what we call suspended growth. And we also have another type called attached growth. That is the organisms, they are attaching on the surface of the media. For example, here for the moving biofilm reactor, the MBBR carrier. So these microorganisms, they attach on the inner surface of this carrier. And here you can see some different color shaded microorganisms here, and they are forming a biofilm on the surface. So these are the two major types of different reactors in designing biological wastewater treatment. Today we'll have a very a touch of the different types of bioreactors that we're going to talk about in the following slides. I believe in the next two classes, Professor Jiang will have a more detailed introduction of different types of reactors. Today we just have a brief introduction of these reactors. So the first one, oxidation ponds. So here, although it's cold-tech solutions, but in waste treatment design, it's not always go for a high-tech solutions. Low-tech solutions does not mean it doesn't work. Each treatment process will always have its pros and cons, and you need to, if you are designing a wastewater treatment plant, you need to consider how much land you have, or the operation cost of each process, the capital cost of each process. Then you can decide which process is the most suitable process for your biological treatment. It's not always go for high-tech solutions. So oxidation ponds, by types, it can be aerobic ponds. That means there's oxygen dissolved in the water, and anaerobic ponds. That means there's no oxygen, and facultative ponds. The ponds could be converted either aerobic or anaerobic. It depends on the operational needs. So for aerobic ponds, it's typically a shallow pond with a less than 1 meter deep. So in this pond, it's a combination. It's kind of mimicking the natural decomposing process of the organics. So we have algae living on the surface, and some plankton and microorganisms in the water body. So the organics in wastewater, when they are discharged into these water ponds, and the organics decompose the organics using oxygen. And algae on the surface with the sunlight and the photosynthesis, they're generating oxygen for the use of the microbes in the water. So because the ponds are very shallow, so they need to have a large footprint requirement if you want to treat the wastewater compared to the activated sludge that we'll be talking about. So activated sludge is kind of like a enhanced version of oxidation, the aerobic ponds. In this process, we use a mixture of wastewater and the microbes, and we blow in air to provide the oxygen for the microbes. So like here is the reactor tanks. In this activated sludge, we have sludge suspended in this reactor tank, and with air blowing into the reactor, and we provide sufficient oxygen for the microbes to decompose the organics. So the organics is consuming this consuming why it's called activated sludge. That's kind of like where we are giving it air, we're giving it source to activate their decomposition mechanism for there to remove the organics. So the typical how much of the organisms we would expect in a typical activated sludge tank, that would be 2,500 milligrams per liter in designing a activated sludge tank. In operation, it may varies depending on how much of the return activated sludge is returning. So here, after the major reactor tanks, the aeration tanks, then it's the sedimentation tanks. Sedimentation, we separate the liquid with the biomass, and the biomass is being either wasted or returned to the bioreactor, because we need to maintain, because when the wastewater leaves this reactor, it also brings the all microorganisms with them, and in this sedimentation tank. So when the microbes settle to the bottom, the sludge settle to the bottom, and then we can determine how much of them we want to return to the major reactor, and then we can control. This is the way we control how many of the microbes will be kept into the reactor. So the activated sludge process, it's the most commonly used process, and it's also a very reliable process. I think it has been developed almost like 100 years. So it's a very solid process that we can use for wastewater treatment. So here we are looking at the Sartin wastewater treatment plant in Hong Kong. So here we can see the oxidation tanks, aeration tanks. That's how it looks like in real wastewater treatment plants. So you see the white bubbles on top of the water tanks. That would be the aerations. That would be the oxygen is being blown into the system. So the Sartin wastewater treatment plant, a little more background of it is that it has been operating for almost 40 years. I think it was commissioned in 1982. It has been serving the Hong Kong people for 40 years for now. So oxidation ditch is kind of like also similar. It's also using the activated sludge process, but with a revised shape of the tank formation. So as we see here, in typical aeration tanks of activated sludge, they're rectangular, and in here oxidation is in oval shape, and in here the water flows like this, and then you have a longer detention time of the wastewater in here, kind of like you have more time for the contact between the organics and the microbes, so they can remove more of the organics. But the thing is that if we use this, we may have a problem with that. We may need more land required for the designing a wastewater treatment plant. So in designing, it's always a comparison of different process. Each treatment process have their pros and have their cons, and we will need to select the most suitable process for each wastewater treatment plant. So another suspended process is membrane bioreactor. So the membrane filtration process, I believe you have already have the last one or one before that. So the membrane bioreactor relies there are two parts of it. The first part is the aeration tank. So here you have the aeration tank is also doing the same thing. We have the aeration blower working here, providing the oxygen for the microbes to decompose the organics. And the organics here, and the next. But what's different from the activated sludge process is that it does not require a sedimentation tank to separate the solid from liquid. Here we have a membrane process. So the membrane, you apply pressure over it, and you force the water passing through the membrane, and you have the membrane blocking this activated sludge from entering the channel, and you have the permeate water and leaving the system here. So with this membrane bioreactor compared to activated sludge, because there's no need for a dedicated secondary sedimentation tank, it saves a lot of space. And also here the biomass in these systems, the concentration is much higher than those in activated sludge. Could reach in the biomass in activated sludge is 2,500 milligrams per liter. Here could reach 6,000 to 8,000 milligrams per liter. And here we can have a smaller aeration tanks and also save space on the separation of the liquid and solids. So, but the thing is that the membrane MBR process, it requires it's more intense in energy input, because not only blowers you need to provide oxygen, you also have a pressure applied on the membrane for the filtration process. That's why it's more energy intensive. And here this figure is looking like how the membrane looks like in actual modules. They will just soak into the water tank underneath it, and the water will be passing through the membrane in here, pass through the modules into the middle of these membrane modules, and then leave the system. So for membrane bioreactor, it's one of the project of ACOM and DSE. So DSE is the Drainage Service Department of Hong Kong government, and it is in charge of all the wastewater treatment plants in Hong Kong. And here the Wuhui effluent pollution plant is located to the north of the Hong Kong area, and there is a membrane bioreactor installed in here. So the thing about the membrane, this is the project of upgrading the existing Wuhui effluent pollution plant that we were talking about. So Wuhui effluent pollution plant has been also commissioned since its commission. I think it's also in the 1980s. It has been commissioned for almost 40 years for now, and in 2010s, and the original plant has already almost reached its design capacity of 70,000 cubic meters per day of the design capacity. So DSD has determined we need to expand the treatment capacity of the Xiaohuhe EPP. So Xiaohuhe, it's so, but the problem is that we only have very limited space, but we need to increase the treatment capacity. So we don't have more space to expand to build more more aeration tanks for activated sludge. So what we did was that we used the Xiaohuhe is using the MBR membrane bioreactor in the system. So but it's under construction and could be it's the upgrading work is expected I think in 2030 something. And after upgrading within the similar footprint, they can double up the treatment capacity. Originally, it was around 70,000 cubic meters per day, and after upgrade using the membrane bioreactor from upgrading to MBR from activated sludge, it can reach the almost 190 cubic meters per day of treatment capacity. So within the similar footprint, it doubles up the treatment capacity. So that's the, but of course, we'll have more energy input into the system. So another emerging or say innovative technologies in suspended system is called aerobic granular sludge. So aerobic granular sludge is different from suspended activated sludge in the form of the microbes. You see here the microbes, they are in size of granules in micrometer scale. They suspend much faster compared to the activated sludge. And you can watch this video and have a clear difference. Okay, so the AGS system is the proprietary system from Narita. So aerobic granular sludge here. Okay, so the left one is the aerobic granular sludge, and the right side is the conventional activated sludge. You see the sludge here is already in granular form, and it's suspended. What they're doing is a settlement test. See how long from this sludge to settle. You see, then we can watch this video. So you see the aerobic granular sludge, AGS sludge, they settle very fast. Like within 10 seconds, all the sludge is already settled. That will save a lot of time on. They will increase a lot of the treatment capacities of this wastewater treatment plant. But here in the conventional activated sludge, you see it takes much longer time for them to settle down and to separate the liquid from sludge. See, in this design, so after 20 minutes, the activated sludge reached the same level of this as the AGS sludge. Okay, so with this new emerging new technologies, innovative, we can reduce the treatment system footprints, and footprint especially the footprint issue is very a big concern in the designing of local Hong Kong wastewater treatment plants, because we always don't have enough footprint for the new wastewater treatment plant to be built or some new upgrading of existing plants. So with these new technologies, we can decrease the treatment system footprints and then we can increase the treatment capacity of the plant. So this AGS system will be applied in the Yunlong effluent polishing plant. So the Yunlong effluent polishing plant will be the first plant in Hong Kong using the AGS system. So here, this is the upgrade job. All right, sorry about this. Okay, so here are the Yunlong effluent polishing plant, the first plant in Hong Kong adopting AGS system. So the existing Yunlong sewage treatment works. It's a plant like this. It was originally commissioned in 1980s. It has been operating also for 40 years. And the problem is that when we are doing the upgrading of the Yunlong effluent polishing plant, we have to kind of double the treatment capacity within the exactly same footprint. So this cannot be done with the conventional activated sludge. So this is why we say we have to rely on some new technologies, more advanced technologies, and then this work's being constructed and under constructed and expected to be done in 2027. And so this is the divisions of the future Yunlong EPP that we'll be looking around. So here we have around like also around 70,000 cubic meters per day of the treatment capacity. And here after upgrade with AGS, we can with exactly the same footprint, we can reach the 150 cubic meters per day, 1,000 cubic meters per day of the treatment capacity. So also the upgrade works is true. Also here you can see all these in the old days, the wastewater treatment plants, all the tanks, they are exposed to the air, and some of them may have the we have the odor issues if there will be some there will be people living around this area. So in the upgrading work, this will be done. Most of the treatment tanks will all be enclosed in the building. Therefore, we have a better control of the odor issues along with the treatment process. And also in Yunlong EPP, they have all the UV PV panels installed for generating the energy and also anaerobic digesters. So therefore, the Yunlong EPP is said to be an energy neutral plan to be built in Hong Kong. So the stage 1 work is done by DSD and us. Will be expected in 2027. Okay, so that's pretty much for the suspended solids. And let's take a break. And after the break, we will have the introduction of the another form of the biological treatment for attached growth. Okay, we'll be back in 10 minutes around 8:25. Okay, let's get back to the class. So we have just finished the suspended growth systems, and next would be the attached growth system. Attached growth system, it would be those. So the microbes, they will attach on the surface of media, could be any media, to form a biofilm, and for there to do the biological treatment. So for biotrickling filter, remember, it's not an actual filtering or seeding process. This is a biological treatment process. So the media, the material in this trickling filter, as you can see here, we have this is the configuration of a trickling filter, and we have different media, different types of media in the system. Could be rocks, could be sand, could be some of the plastic media that we talked about here. And here, so the microbes, they attach on the surface of this media, forming a biofilm, and you see the influent of the wastewater is being pumped into the system. There is a rotating arm, you can see here, and these arms can be discharging this influent wastewater to the system, and the water flows through this media and leaves the system at the bottom. That's how they treat. This is how trickling filter works. So this is one of the attached growth systems that we talked about. And another type is rotating biological contactor, RBC. So this was used mostly in old times, and but still in nowadays, now we have more like advanced technologies like a moving biofilm reactor that we'll be talking about later. They would be more preferred today nowadays than the RBC, but this still has its applications, especially in some rural areas. When we do not need a centralized or large wastewater treatment plant, they can be applied in a small scale systems. And this RBC system, it consists of a series of closely spaced discs on a shaft rotated, and 40% of the disc is submerged. Like this, you can see you have a disc of the biofilm attached on the disc of these systems, and they're rotating, and this 40% of the disc is contacting with the of the organics, and here the attached microorganisms on the surface of these biological reactors. Then this film fixed on the surface and contact with the organics takes up and then treat the wastewater, and with aeration, of course. So that's how rotating biological contactor is working. And for nowadays, we have more advanced technologies like moving biofilm reactor. It's very commonly used in modern wastewater treatment plants. So what is moving MBBR? So MBBR is the reactor that use of these plastic carriers. A lot of carriers suspended in the reactors. The reactors could be aerobic form or anoxic form. So in aerobic form, the plastic carriers, because their density is smaller than water, they can suspend it in water easily with the with the aeration. So the aeration with air blowing in the mixtures they are mixing together, and these carriers, they have these biofilms grow on the surface of these materials and performing the degradation of organics. So with the biofilm on the surface of these materials, the organics, they need to intrude the biofilm. What is biofilm? Biofilm is the community of different organisms, microorganisms, on the surface of the carriers. So the organics intruding, diffused into the biofilm and being degraded, hydrolyzed, degraded, oxidized, and released. So here is the biofilm compared to the activated sludge is that it's more, it does not require return activated sludge, because as you recall, when we're doing the activated sludge process, we have a return sludge because the biomass is leaving the system, and we need to separate the biomass from the wastewater using a clarifier. But here in MBBR reactors, these biofilms, the microbes grow on the surface of the carrier, and we have a sieve on the edge of the reactor when only wastewater can pass through. The carriers retained in the reactor. These carriers does no flow with the wastewater. So therefore, it is a very compact design compared to the conventional activated sludge. Also, the biofilm, the biomass on these carriers could be much higher. So the overall biomass in the reactor could be much higher than the conventional activated sludge. So here, this is another project that DSE and ACOM has been working, and this is the relocation of starting sewage treatment works to Caven. So here, this is the starting sewage treatment works that we just saw, and it was originally using the activated sludge process, and it has been commissioned from 1980s. And you can see from this aerial photo, you can see that indeed this starting sewage treatment works is in a very close proximity of these living areas. You see all the people here. So therefore, people have been concerns about like the older issues that I was talking about, and also some landscape issues. Also, this plant has been running for like 40 years, and the facilities is aging, and therefore the DSE has did a survey and decided to relocate this starting sewage treatment works into this cavern next to it. So the whole plant will be moved into the cavern, and the public cannot see this plant is working. So this is one of the iconic projects in Hong Kong, especially for DSE. And here, the problem with the relocating of starting sewage treatment work is that here in this original site space, we have like around 28 hectares of land that is available. But after moving into the caverns, we only have half of the space, only 40 hectares available. So and the problem we need to, even with smaller footprint, we still need to maintain the same treatment capacity of 340,000 cubic meters per day, same capacity, 50% of the footprint. So that's why in the end we decided to use this more advanced MBBR moving by biosystem, moving by biofilm reactor systems for the treatment of biological treatment in this cavern. So you see, this is some of the benefits of some new technologies that has been using in nowadays water treatment plants. So some more typically we could have more compact design, more biomass, higher efficiency, but also we have some pros and cons as well. And because it may require more energy input, some kind of thing like that. So each treatment process has its pros and cons. We need to evaluate on it when designing a wastewater treatment plant. We need to consider all the factors that might be concerned. So in most cases in Hong Kong, land supply is always a problem. We always don't have enough land for the treatment of wastewater treatment. So that's why we can rely on some more advanced technologies to do the work. So after biological treatment would be the secondary clarifier. It would be similar working principles as the sedimentation tanks that we use in primary sedimentation. So the old approach in the old days, the concepts of wastewater treatment is that we want to remove as much as possible. We want to decrease and settle out as much as possible, such as clarifier, because clarifier is cheap compared to a membrane, such as membrane filtration process and other things. Clarifier is using gravity, so it's a cheap one to build. And we use bacteria to remove the organics and want to remove as much as possible and skim out oil and grease and the nutrients because we want to remove them from wastewater, such as the conversion of nitrogen to ammonia nitrogen to nitrate and eventually to nitrogen gas and remove from water and also remove the phosphorus. This nutrient thing, we will have another class talking about this in November. And this is the whole idea of wastewater treatment. But now, as people realize more, the wastewater treatment plant is more of like a resource, rich, abundant resource center. So we would like to recycle as much as possible. So all the organics, or the sludge, when they are being settled out, we send them to anaerobic digestion. Anaerobic digestion, we can decompose the sludge and produce biogas. Biogas can be used to produce electricity, produce heat, and that's how we reuse the resource in wastewater. And also, if possible, we can use anaerobic bacteria to remove organic matter. This would be a slower process compared to the aerobic process. But aerobic process, we need air. We need to blow in air. It's a lot of energy consumption. So in some typical activated sludge plants, so the energy consumption or the operation cost could be around 50%, up to 50% is used for the aeration tanks. So also the oil and grease can be recovered, nutrient recovery, reuse. So the concept has changed nowadays. We want to reuse, recycle what's in the wastewater for our further use. So one of the example that is we can see how they reuse water is the new water from Singapore. So we can watch this video and have an understanding of the background of the Singapore new water. Okay, so here the new water is one of the examples that the wastewater treatment plants in the world is trying to recover as much as possible, as reuse as much as possible. So for Singapore, they have their issues of like a limited water supplies. So they're just trying to recover every drop they use. So from wastewater, after proper treatment, it can be reused. So that's the concept of the new concept here. So also in Hong Kong, local Hong Kong, so in the designing of new wastewater treatment plants like the Yulong EPP, Yulong effluent polish plant that we're talking about. So it also involves a lot of the energy recovery resource. So for example, the anaerobic digestion, they have for the Yulong EPP, they have designed the incorporating of the food waste and the sludge co-digestion to generate more biogas. Therefore, the more biogas can produce, and then this biomass can be used to produce heat, and also for electricity. That's how Yulong EPP has become one of the iconic projects in Hong Kong that it could achieve energy neutral in its design. So that means that the energy produced from the plant is equal to or larger than the energy being used in the wastewater treatment plant. So wastewater treatment plant is a huge energy consumption center because a lot of aeration, blower, and also the pumps, all these things, steamer, a lot of resources are being used here, energy being used here. So the new concept is that we are trying to recover everything, as much as possible from the wastewater treatment. Okay, so the last part of today would be the wastewater quality standards. That means to what extent we shall treat the wastewater. So the standards of wastewater treatment varies from different regions, different states, different countries, and the location and also the receiving body of the wastewater being discharged. So here are the United States as example. So the national standards for secondary treatment, they have characteristics of discharge on the BOD. So the organic concentration is 30 milligram per liter on average of 30 days, and 7 days cannot exceed 45. And also suspended solids. So the major parameters need to be considered in treating wastewater. Here are the pH always around neutral, 69, and here are the carbonaceous biological oxygen demand. And in mainland China, so we have different discharge standards. So level 1 standard, level 1A, level 1B, and level 1, 2, 3. These different treatment levels apply to different wastewater treatment plants and depends on where is the receiving water body of the wastewater being discharged. So major parameters need to be considered is COD, BOD, suspended solids. So these are the fundamentals. And oil, surfactants, and total nitrogen, and ammonia nitrogen, and total phosphorus. So phosphorus, nitrogen, nutrients. So the major parameters always consider is this, and color, pH, E. coli. And some of the, depending on where you're discharging, also you have you have other permissions on discharging on the, especially here, these metal ions for industrial wastewater and these metal ions. And in Hong Kong, effluent standards in Hong Kong. So you can refer to the Water Pollution Control Audience Technical Memorandum on Effluent Standards published by EPD, Environmental Protection Department of Hong Kong Government. So this would be the reading assignment of this class. So in this audience, the audience limits it sets the limit that make effluents acceptable into foul sewers, stormwater, island waters, and coastal waters. So depending on where the water is being discharged, they have different standards, like pH, temperature, COD, BOD, all these parameters to be considered. And depending on where you're discharging, you have different, and the flow rate, of course, and you have different standards you shall follow. So for the wastewater to sewage wastewater treatment plants, it will be foul sewers. So you can read the memorandum, the audience, and then find out what would be the standards for effluents discharged into the sewers leading to our wastewater treatment plants in Hong Kong. So I'll give you an example to have an idea what the wastewater treatment plant in Hong Kong is working on. So here the left table here is the typical composition of untreated domestic wastewater. This is an average, not necessarily the Hong Kong case, but it's an average of some commonly seen concentration of the wastewater characteristics. So we have alkalinity, and BOD is the organics, and COD and chloride. Also here the chloride is a unique feature in Hong Kong, and sometimes because in Hong Kong the chloride could reach up to like a 6,000 to 8,000 milligram per liter. This is because that in Hong Kong, in some areas we use seawater for our toilet flushing. So seawater is a lot of chlorides over there, so that's a concern. That's a very unique feature in Hong Kong. Some area of Hong Kong we use the seawater that have a lot of chloride, and some still use fresh water. Then the chloride would not be a concern. So chloride is could lead some corrosion issues to the equipment, that's mechanical equipment used in the treatment plant. Also, the influent have some suspended solids, and here we have TKN. So TKN is the sum of organic nitrogen plus ammonia nitrogen, and we have phosphorus. So here we are looking at another project of DSD and NACOM. So the effluent polyethylene plant located in the Yulong area. So this new plant is being designed and constructed and will be expected in 2031. So the treatment level of Hongshui EPP is secondary plus with a treatment capacity of 1,000 cubic meters per day. So the BOD effluent discharge being allowed to discharge is at 20 milligram per liter at 95 percentile. So consider this from 200 to 20 milligram per liter. In the wastewater treatment plant, we need to remove more than 90% of the organics before it can be discharged. And I can tell you that in our design, it's way more higher than this. So here is an example, and have an idea what is going on in the wastewater treatment. So the wastewater effluent standards for suspended solids will be 30 milligrams per liter, and ammonia 2 milligrams per liter. So here in the TKN, ammonia, TKN, so the ammonia is being oxidized first into ammonia and then to nitrate and nitrite. And if you want to remove them from wastewater, we have denitrification, and the removal of this process, we will have a more detailed introduction later on. And total nitrogen of 10. So in here, Hongshui effluent polishing plant, because the secondary standard, we do not have the limit on the discharge of total phosphorus. So phosphorus is also a concern. So if the treatment level reaches the tertiary level, for example, Yulong EPP and Wuhe EPP that we have been talking about. So these two they have a requirement for total phosphorus being discharged as well. So it really depends on where will the treated effluent goes, and then we will have different standards for the treatment level. So in this EPD's memorandum, so we have a discharge license for different things. So this license for different when the water discharging body need to discharge their water, depending on where they are discharging and what is going on with their industry or household using. And the license contains terms and conditions specifying the requirements of the effluent discharge, such as where you should discharge, how much, and what is the quality of the effluent you should discharge. And also they have standards for sampling points and set up monitoring points require. You make this test could be done by EPD officers or some other officials to make sure that the license is the discharging water is agree with the license they have. So this would be the reading assignment of this week, and the technical memorandum standards for effluent discharge into drainage and sewer systems in Hong Kong. You can find this in EPD's website. So I think that's pretty much for the class today. So before we finish, any questions? Okay, no. Just a question of mine. Anyone is interested in joining the industry after you finish your degree? Anyone is interested in joining the engineering field? Have any idea of what you're about to do in the future? So I mean, you are taking class of wastewater engineering or water treatment. Anyone is interested in joining this field and have any idea of what you will be doing in the future? Okay, never mind. So if you have any questions, you can come to me, and or you can contact me at this email I showed at the very beginning. You can either email me, or you have questions, you can ask me here. So that's pretty much it for today. Thank you.
那你们现在今天是第8周，你应该讲到了，讲了。哦，OK，那应该。对，如果你是做 audit 比较直接，audit 的其实你就想标准，对，会造成吗？对，我突然今天有给你们那个一些，因为它是多本可以写，你就扫描上面。就是它实际上它有 audit report 呢，这里写，这就是我们这一套，这个是要进行事实的，它里面给你，这边里面导演，发现是就比较精确的一些那个，所以说我懂发生，对吧？
都是他们都会直接导致这个数据的。我们还换了，因为之前的公司导出访者，大部分都好。
你就是那你去掰这个，你就因为这个现在这种程度呢，都是大家对吧？你不可能因为你有真的想去做，但是你去想，现在就是说，你我觉得我们教他呢，也是 formality， 这个市场你要是一个专业的。第二呢，就是你的获利是你的质量数据质量还有其他的这些指标。现在市场真的没有，我或者觉得信息，现在大概做些什么？
我感觉你们是你朋友。
那比如说，现在你去做 audit 的话，你就看他你 audit 的数据，看他说